Hello everyone. We will start to talk about the transformers. So you can see a simple transformer figure here. We have a ferromagnetic core, then primary winding and secondary windings are located on the left and the right side of the ferromagnetic core. So we will discuss how the system will operate and then we will try to obtain the equivalent circuit of this practical transformer. So the system starts with the primary voltage supply. So after we apply the voltage to the primary winding, we can see the IP, which is the primary side current, which is flowing through the primary winding according to Ohm's law. So the first operation in here will be the consumption of the current losses, I square losses on the primary winding because of the resistance of the winding. Then this IP will produce magnetic field intensity, which is around of this winding. So with respect to Ampere's law, we will see the magnetic field intensity H around the winding. Then we can transfer it to the core, ferromagnetic core, according to permeability value of the transformer, ferromagnetic core material. Then with respect to cross-sectional area, we can produce the flux inside the magnetic field and inside the magnetic core, and we can transfer to the secondary side. So inside the ferromagnetic core, we can see the flux, which is the equivalent of current in electric circuits. Then for the secondary side, a voltage can be induced with respect to Faraday's law. So this is the simple operation of the transformers. But when we examine the losses, as I said, the first loss will be the copper losses in the system because of the windings. But in addition to that, we have a core structure. So for the core structure, we should consider hysteresis and eddy current losses. According to core material, we will see additional losses. And the last loss of the transformer will be the leakage flux caused losses. What is it? So we produce the magnetic field on the primary winding, but some of this flux will flow around the primary winding. So it will stuck around the primary winding and it will rotate continuously. So we can produce a flux, let's call it as phi p. At the primary side, we can produce the total flux, but we cannot transfer it totally. What will happen? Some of the flux will leak around the winding, then we will transfer the remaining part. And we can call that part as mutual flux, which is the connection flux of the primary and the secondary sides. Similarly, for the secondary side, some of the flux must rotate around the winding, and we can call it as phi ls. So for the secondary side, total flux can be written as the leakage flux and the mutual flux. So let's combine all this knowledge to be able to obtain the equivalent circuit. So first of all, we can start with the conversion issue because transformers convert one voltage level to another voltage level simply. So we can use an ideal part to show the conversion ratio between the input and the output side. So let's start in the middle of the circuit, which represents the conversion of the transformer. And between the input and output side, the number of turns can be the critical parameter to adjust the voltage conversion. Or it can be written as VP to VS, or it can be used as A to 1. And here A represents the turn ratio, and which is the ratio between the voltage or the number of turns. So simply the turn ratio can be defined as VP over VS, primary side voltage over secondary side voltage can be used. Okay, what about the equivalent circuit? Let's continue for the equivalent circuit. This is the ideal part, conversion part of the transformer. Then we must integrate the losses. Which losses? Let's start with the windings. So for the windings, the copper losses will be active. So for the copper losses, we can use resistances. For primary winding resistance, we can use RP. And similarly, RS can be used, which represents the secondary side winding resistance. What else? We have leakage fluxes around the windings. We called as phi LP and phi LS. When we examine the flux issue, it has 90-degree phase difference with the voltage. So because of this, for all flux-related losses, we will use inductances in the equivalent circuits. So for the primary and the secondary side, we can use XP, which represents the primary side leakage flux losses, or similarly phi XS, and it represents the reactance due to the secondary leakage inductance. Okay, so we can add some details. For example, VP, which is the primary side voltage, IP, primary side current, and similarly IS, which represents the secondary side current, and VS, which is the secondary side voltage. What else? These four parameters, RP, XP, XS, and RS, represents the winding related losses. But in addition to that, we have one more system inside the transformer, which is the core. For the core related losses, we will use a branch, parallel branch here. The reason of this one, initially the system doesn't have to be supplied the load, but initially to be able to operate the transformer, we have to satisfy this correlated losses, correlated power requirements from the input side. So because of this, it is represented at the primary side. And for this parallel branch, we have two components. They will be resistance and one more reactance. Resistance is the RC, which represents the core losses inside the transformer, and these are hysteresis and eddy current. In addition to that, so totally they represent the core losses. In addition to that, we have one more component, which is phi XM. And we need this component to obtain the phi M, which is the magnetizing current of this transformer. So if we can create this phi M, it will be the main parameter to obtain the phi M, which is the connection flux for the secondary side. So when you want to obtain the secondary side voltage, according to Faraday's law, you need to obtain time varying mutual flux. It will be the main parameter for the secondary side voltage production. Of course, after we eliminate the losses inside the system. So this is the two-sided equivalent circuit of the transformers. So we will apply some simplifications to the equivalent circuit to simplify our calculations. For example, this is the two-sided equivalent circuit. So we have two different voltage levels because of the primary and secondary side voltage. But in each voltage or current calculation, we need to use this conversion ratio, term ratio, to be able to convert secondary side parameters to primary or primary to secondary side. So let's apply this variations conversion ratio inside the equivalent circuit. For example, we can refer all the equivalent circuit parameters to the primary voltage level. So what does it mean? We will use all the components at the primary side. So for the primary side components, we can draw them directly. For example, RP, XP, RC, and XM. These are the primary side components. What else? We have VP and IP, which represents the primary side voltage and current. Okay. Which parameters remained? XS and RS. For these components, we can transfer them to the primary side. We want to eliminate this middle part, conversion part. So we can use one reactance and one resistance, but we change their places. So we will call as primes, and we must keep the equality of the previous equivalent circuit and this one. What about the voltage? We are writing each parameter with respect to primary side voltage level. So because of this, A times Vs will be Vp in the equivalent circuit. Or similarly, Is over A can be used according to term ratio. What about the prime parameters, Rs prime and Xs prime? So what we did, we transferred the secondary side parameters to the primary. So we carry them from the secondary side to primary, or right to left. In that case, we must multiply their initial values with the term ratio square. So A square XS can be written for this parameter new referred sites. Okay, so this is the first version, referred to primary voltage level, and we can repeat the study for the secondary voltage level, and it will be more important for the calculations because we are connecting the load to the secondary voltage level in our calculations in the practical cases. So secondary voltage level examinations are more important for the real side. Okay, so let's refer all these parameters to secondary voltage level. What will happen? Let's start with the secondary voltage level for this case. So we will start the reactance and the resistance. That means XS and RS because we are working on Vs and Is. Then we will refer our primary side components to the secondary side, so their values must change with respect to secondary voltage level. So because of this, we have RP prime, XP prime, and for the excitation branch, parallel branch, we have RC prime and XM prime. So instead of 2, we have 4 parameters for the secondary voltage level referred case. And for the primary side voltage, we have Vp over A, or for the current, we have A times Ip. Okay, what about the prime values? For the prime values, instead of with the multiplication with a square, our direction has reversed. So because of this, rp prime, xp prime, rc prime, and xm prime can be calculated from their initial values from primary side equivalents by multiplying with 1 over a square. So if you multiply with 1 over 8 square, you can find their secondary voltage level referred values. Okay, so we have one more simplification. So we eliminated inside the two-sided equivalent circuit the conversion representation. Then we have one more simplification. What is it? It is about the excitation branch, about this part. So we have two components, RC and XM, or RC prime and XM prime. But when we examine their values in the real practical applications, the RC and XM, they have very big values with respect to series components RP, XP, RS, and XS. So if their values are too big when we compare with the others, that means the current flowing through that branch will be very, very small according to other part. So because of this, let's slide that part, that excitation branch, to different points of the circuit. Why? For example, if we have connected a load to the output part, what will happen when we want to calculate the total impedance value? First of all, we have a series connection, then parallel connection, then one more series we have. So instead of this, if we slide that excitation branch to the beginning of the circuit, what will happen? First of all, we have big series connection of RP, XP, XS, RS into load. Then it will be connected in parallel with the excitation branch. So by using the smaller current difference for the excitation branch, let's obtain the approximate equivalent circuit. For approximate equivalent circuit, also we can examine the same system for primary voltage level referred and secondary voltage level referred cases. So let's start with one of them. For example, what will we do? We will start with the excitation branch with RC and XM if we are working on the primary voltage level, because RC and XM original places are the primary. So if we are working on the primary voltage level, here we have VP and IP. So what are the remaining components? We have two resistances and two inductances which are connected in series. So let's combine also them. So we have our equivalent primary and X equivalent primary if we combine all the remaining parameters. Okay, so RC and XM, they are obvious, they're original primary equivalents, but for the equivalent resistance and the reactance, we have RP, which is the primary winding resistance, and we have A square RS, which is referred to the primary side from the secondary. And similarly, XP and A square XS will be the X equivalent primary side equivalent reactance, which is connected in series. So this is the first case for the approximate equivalent circuit, which is referred to the primary voltage level. And similarly, we can refer that circuit for the secondary side. So the next one will be again we will refer to secondary voltage level. And we are working on the approximate equivalent circuit. Actually, the circuit is exactly the same. What does it mean? Again, we have one resistance and one reactance, the excitation part, then resistance and reactance will be. So in terms of circuit diagram, they are exactly the same, but our parameters will change. Why? Because now we're working on the secondary voltage level. So because of this, we must use their secondary equivalents. For example, we must use RC prime and XM prime, because without prime, we have the primary values, but now we change their places to the secondary side. And for the series part, we have our equivalent S and X equivalent S. So again, the total winding resistances are combined for the secondary voltage level, and similarly for the reactance, we can repeat the calculation. So we have Vp over A and A times Ip for the secondary voltage level equivalence of the primary side. And for the secondary equivalents, our equivalent S and X equivalent S. What we have now, we are working on the secondary side equivalents. That means we will use our S and XS directly, and primary side resistance and reactance must be referred to the secondary side. Okay, this is the last version of the equivalent circuit for the transformers. So we have different cases, but commonly approximate equivalent circuit versions are used, and for the secondary voltage level referred case is used for the calculations because of its simplicity, and it is easy to adapt for the real applications. Thank you for watching.